So we left off here on Tuesday on slide 300. And we're going to discuss some of the issues with distance vector routing problems. I guess the first point to make here is that understand that these problems have all been solved. But I think it's good to kind of understand history. It gives you kind of an understanding of why things are the way they are today. So we'll talk about the count to infinity problem, routing loops, and then several fixes: hold down timers, triggered updates, split horizon, poison reverse, and route poisoning. All right, so here's the count to infinity problem. Router A is advertising this 1, 2, 3, 4, 5, 6, 7 network to router B. And this would be specifically to RIP. So the routing protocol RIP, you would announce your updates to your neighbor on a timer, and it would be every 30 seconds by default. And router B is going to announce all of its updates to router A on a timer, but they don't synchronize these timers. So imagine that A has 25 seconds left on its update timer for B, and B has 5 seconds left on its update timer for A. So A has told router B in the past, I can get your traffic to 1, 2, 3, 4, 5, 6, 7, and it's 1 hop away. And B has installed that in its routing table. And then B told C, I can get you to 1, 2, 3, 4, 5, 6, 7, and it's 2 hops away. Now, A loses this network. This interface goes down. So it needs to tell B that the network is down, but it's going to wait until the next update timer to do that, 25 seconds from now. In the duration, 5 seconds elapse from B's update timer, and it advertises all of its routes to A. So A then installs that it can reach 1, 2, 3, 4, 5, 6, 7 by sending packets to B. And we can see that that's not true, but the routing protocol here doesn't know that. And this is going to cause a routing loop. I like to call this opposing gateways. A believes that B is the owner of the 1, 2, 3, 4, 5, 6, 7, and B believes that A is the owner of that network. So when they have traffic descend, it's just going to bounce back and forth between the two routers until that TTL expires. So now a worse problem happens here. The next time that A announces it to B, now A's cost has changed. A's cost is now 2 hops. So since B could get there in 1, it says to A, I could get your traffic there in 2 hops. So A is going to update its table to 2. And then on the next update interval to B, it's going to tell B, I can still get you there, but now it's 3 hops. And when B advertises back to A, it's going to be 4. And this is just going to continue to count to infinity. Now, the problem is there is no infinity value in computers. The programmer that had written this code set aside an amount of memory to hold that value. And when that gets exceeded, the router crashes. So in order to fix that problem, they defined infinity. They defined a maximum of 16 hops. So they will count no further than 16. And then after, looking at this for a while, they said, every time we see a 16 here, there's a problem. And then we can leverage that. So now when A sees the network go down in the first place, it would then advertise the route to B as being 16 hops away. So we see here that there'd be a routing loop because the two routers believe the other is the owner of that network. We prevent routing loops with several things. The first of all being what's called a route poison. Route poison is when A says to B, that network 1, 2, 3, 4, 5, 6, 7 is 16 hops away. Now, another rule we have here, the rule of split horizon, helps solve this route looping problem. Once B accepts the route from A in the first place, B is then prohibited from advertising that route back out that same interface that it learned the route on. So the rule of split horizon says I may not advertise a route back in the same direction in which I learned that network. So it's the don't tell me what I told you rule. So if A advertises the route to B, B accepts that route, B cannot advertise that same route back to A. So this route poisoning is the way that we lift that rule. Now A can't get there anymore. If B knows another way to get there, A would like to know that. So by sending the route poison, B is saying you are now released from the rule of split horizon. You may now advertise to me how you reach that. So B is either going to announce another pathway that it has, or it's going to reverse the poison. So reversing the poison is B saying, you're right, it's 16 hops away. So then they would both agree that the route is unreachable. So another feature that makes this go faster is triggered updates. This is where A will tell B about this change immediately as soon as it detects the network is gone, rather than wait for its update timer. Now, in these days, we had very unstable interfaces. It was common for an interface to just go up and down and up and down. We called that a flapping interface. And these CPUs weren't so powerful back then, and a flapping interface would cause a lot of trouble with the machine. Maybe the machine would even crash if the interface is cycled up and down too fast. So they institute a timer called the hold down timer. So now when A poisons the route to B, if B doesn't have another route to get there, it puts the route into a hold down time. And that says freeze your routing information for a duration of the hold down timer. And in RIP, the hold down timer was 280, I believe. 180 seconds. So you got 3 minutes of time here. Whether if there is another way to get there, B's not going to listen until the hold down timer expires. So hold down timers are something that you see in RIP, but you don't see in EIGRP or OSPF. Hold down timers are why a routing protocol would take minutes to reconverge rather than seconds. So we expect that RIP will take minutes to reconverge. That's not necessarily good. And in OSPF or EIGRP, you expect seconds for reconvergence, which is better. So none of these things are as important in EIGRP or OSPF as they were in RIP. So you still have a split horizon rule. That's important. You still have the idea of route poisoning, but because of their speed of communication, then it doesn't cause the long delays like it did in RIP. So link state protocols, updates are triggered when topologies change, not on some timer. So we have a formal hello protocol, link state routing protocol and EIGRP. They become neighbors by exchanging these hellos. And then you don't have to advertise the routes on a timer. In RIP, the only way a RIP knows about other routers is to receive their routing updates every 30 seconds. So rather than advertise the entire table every 30 seconds, now we're just saying hello on whatever our hello timer is. Like typical hello timer in EIGRP is 5 seconds with a hold time of 15. So OSPF is 10 seconds for the hello and 40 seconds for the hold time. So they are better at getting the message out. They're faster to reconverge than the older protocols. Now, link state, it says uses less bandwidth than distance vector. And that would be a factor of them not advertising their entire table on some timer. So that's a yes and no, right? There would be during their initial neighborship, when they first become neighbors and they first synchronize all their routes, they're going to use quite a bit of the bandwidth, maybe all of it. And then after they're finished synchronizing everything, they'll settle down and they're very quiet. All they do is say hello based on the hello timer. Now it takes more processor to process all of the information. The way we compare distance vector versus link state, it involves roads often. And we said that in distance vector, you would find a sign that pointed you towards your destination and you would go that way without really understanding exactly where you're going to go or all the turns you're going to make. And then with link state, the analogy would be you have a map of the network and you would find on the map which way you were going to go. So link state, more effort as far as CPU and processing of databases, storage space to store those databases, but better decisions. Now, OSPF has a very intensive design procedure. You have to design your network the OSPF way if you'd like it to behave correctly. So we say it requires more engineering resources too, right? The people on your team need to understand OSPF and need to be able to support it properly in order for it to be functional. So we become neighbors by exchanging hellos. They build what's called a link state database by exchanging LSAs. Every router is going to have the same link state database when they're done with their synchronization process. And that's restricted to an area, right? If this is all the same area, all the routers have the same database. If there's an area 1, an area 0, and an area 2, then router that participates in all 3 of those is going to have, area 0 database and an area 1 database and an area 2 database. And there's design guidelines, right? Like every non-zero area must have an attachment to 0. And area 0 itself needs to be very robust, right? So the links inside of area 0 need to be redundant. They need to be all the same speed. You can violate these rules, but it's better that you don't. And if you do, you know what you're doing, you can get away with it, but it can cause you some interesting pathways if you don't design it the OSPF way. The routing algorithm here is called SPF, or shortest path first, and that's what OSPF stands for, open shortest path first. Open meaning that it's an open standard. Ideally, or it should be that every vendor's OSPF should get along with every other's. It doesn't work out that way in real life as much as we'd like, but it's certainly possible to run OSPF cross-vendor. OSPF is an interior protocol. It's link state. It's classless. So recall that classless means that the router is going to advertise not only the network number, but also the mask that goes along with it. So anybody who receives that route, they will not have to assume or guess or try to figure out what mask will be used. They are told what mask will be used. So we have 2 different versions of this. Version 2 is for IPv4 networks, and version 3 is for IPv6 networks. So I should say in the beginning here, there's a few different levels of knowledge for OSPF. So there's one level of knowledge you need for CCNA, there's one you need for CCNP, and then there's one you need for CCIE, and then there's one you need for actually working on an OSPF network in production. And I'm afraid they're not all the same. So you're going to get kind of a very basic intro to OSPF here and understand that there's a lot more. I wouldn't be exaggerating much if I told you I spent a year or 2 in the lab with OSPF to get to the point where I needed to be to pass the CCIE lab. OSPF is no joke, and it's a pretty complicated protocol. So I wanted to show you here. I typically do a whiteboard discussion when we get into OSPF. There's a lot of little facts, and many of these are going to be testable, so it's a good thing for us to go over. So if you look in your class files, there's a file there that says OSPF whiteboard talk. So this is one of our drawings that I've done before. So make sure that that updates. Yep, I see that. Yeah, good point. Andrew's mentioning some good OSPF books. Make sure you get the John T. Moy book for him. That's my favorite. All right, so the first thing to talk about is that OSPF runs on an interface on your router. And when it runs on an interface, OSPF is going to qualify the network type, okay? So there's several network types. First of which we'll talk about is the broadcast network type. So that would be on an interface that's Ethernet. And then there's an NBMA, non-broadcast multi-access. So that would be on an interface that's got encapsulation frame relay as a serial interface or as a multi-point subinterface. Not that you'll never see those anymore, but they're pretty rare today. Then we've got point-to-point. Point-to-point would be a serial interface that says encapsulation HDLC, the default, or encapsulation PPP, or a point-to-point subinterface under a serial interface. Those 3 are the only ones that are automatically detected as far as physical interfaces go. There's a couple of additional ones that were useful in the frame relay world, point to multipoint and point to multipoint non-broadcast multi-access. So 2 facts here. I put the 2 broadcast and NBMA together because those are the only ones that do the DR BDR election process. So DR is designated router and BDR is backup designated router. These 2 network types will do that. And the whole purpose of that is explained down here, like 3 and 4 here. 3 synchronizes with router 1, all of its routing information. So their database will be the same. And then 4 synchronizes with router 1 as well. 3 and 4 do not directly synchronize with each other, but because they both synchronize with router 1, their databases are the same. It's something in computer science we call the transitive property. And that's the whole role of the DR functionality, is to cut down on the amount of work that has to be done for all these routers to have the same database. The BDR is the backup. So it's there to take over should the DR fail. You got a backup DR. And only the broadcast and NBMA mode will perform that DR BDR election process. Now, I think this particular style of connectivity is unusual. You know, when do you have a group of routers like this all sharing a broadcast segment? Like, how would you make that connectivity happen? So these 5 routers are either on a hub or they're on a switch all in the same VLAN. And not to say that that never happens, but that's fairly unusual. You'll see it in, like Kevin's mentioning, sometimes in MPLS, it comes up depending upon your MPLS design, and then also sometimes in DMVPN. What you want, however, is the point-to-point. So if you have 2 routers that are connected together with a Ethernet interface, but there's only 2 routers, like you've done a crossover cable to connect them together, or a piece of fiber optics, OSPF is going to treat that as broadcast by default, but it's really point-to-point because there's only 2 routers on the link. So it'll be your responsibility to tell the router that it's a point-to-point interface. And the point-to-point does not go through the DR BDR election process. So while in application, it probably doesn't make a whole lot of difference as to how fast they'll reconverge, it's just proper for you to not do the DR BDR process unless there's more than 2 routers on the link. So I'll go into my interface here and I'll say IP OSPF network point-to-point to force them into this point-to-point mode. Now I have here the default timers that they use. The broadcast uses a 10-second hello, 40-second hold time. The NBMA, 30-second hello, 120 for the hold time. Point-to-point is 1040, then all the rest of them are 3120. So probably even more important for the CCNA exam is this list of items that are in the hello packet. And the stars you see here are all things that routers must agree upon before they can be neighbors. So we start out at the top with AID, that's area ID. So like for router 1 to talk to router 3, these interfaces that connect them together must be in the same area. So it's okay for router 1 to be in more than one area, but on this interface that connects to this router that they share together, the opposing interfaces must be in the same area. Then there's router ID, and how the router ID is chosen is something you'll want to have mastered before exam day as well. So the router ID is the identity of the router, and a router ID must be determined by an OSPF router before it can even talk to any other neighbors. But it's not okay for 2 routers to have the same router ID. The router ID must be unique. The router ID takes the form of an IP address. That is, it's in dotted decimal notation, but technically it's not an IP address. It's a router ID. So you'll see in the slideshow later, but it's worth repeating. The router is going to look into the OSPF configuration for the command router ID. And if that command is there, whatever the command says is the router ID. And in my opinion, you should absolutely set the router ID. You shouldn't leave it to have the router pick its own. If you didn't define the router ID by command, then it would look at all the interfaces on the router, preferring loopback interfaces. So if there are any loopbacks, the highest IP address on a loopback would be the router ID. If there are no loopbacks, then it would be the highest IP address on a physical interface. And those interfaces don't have to actively participate in OSPF to be chosen. They just have to be up. So I think it's really important for the router ID to never change. So when you configure OSPF, you say router OSPF 1. The very next command you do should be router ID and whatever the router ID is. That way the router will know it before you activate it on any interfaces, so that it will not choose its own router ID. You have those timers. So that's what we saw over here. Routers must agree on the timers before they can be neighbors. You can do authentication. That is, you could put a password on their session. They would have to agree on both the method of authentication and the authentication keying material. There's a type of area called a stub area. If an area is stub, all routers that participate in that area must agree that that area is stub. The way the RFC words it, and OSPF version 2 is covered by this RFC 2328, they say they have to agree on the subnet mask, which is kind of a strange way to say they must be in the same subnet. So two OSPF routers on this link that connects them together, they must be in the same subnet here. They must agree on the MTU. If the DR is used in this type of network and this router knows what the DR's IP address is, it will be listed here. If we're on a point-to-point network where it doesn't do DR, you'll see the DR's IP address listed as quad 0. So same thing with BDR. If we know the BDR's IP, then it'll be here. There'll be a list of neighbors, and there'll be a priority value to use in the DR-BDR election. Default priority is 1. Now we have over here the packets that are exchanged between OSPF routers to do all this work. The type codes you see here, type 1, 2, 3, 4, 5, that's how you would see it if you were looking at a debug IP OSPF hello. So you have here hello packet. That's what's used to initially start their neighbor relationship. You have a database description used in the synchronization process, link state request to ask your neighbor for information, link state update for them to deliver it to you, and an acknowledgement to say that you received what they sent you. So the little song I sing in my head here is, hello, DBD, are you alive? Which is 1 through 5. Then we have what they call a state machine. These are the states that OSPF will go through from not being neighbors to being fully adjacent, or neighbors that have exchanged all of their routing information. When two routers are fully adjacent, they will have the same link state database for the area in question. So we start out in the down state. In the down state, the routers are not neighbors. One router is going to send a hello to the other, and that transitions them to the init state. So let's say I send you a hello. My neighbor list is going to be empty. I don't have any neighbors on this interface. You're going to add me to your neighbor list by router ID. Then you're going to return a hello to me. In your hello, I will see my router ID in your neighbor list. And that validates for me that we have bidirectional communication. The only way you would know my router ID is if you got the hello packet that I had sent you. So we're then in the two-way state. Now, if we're doing a DR-BDR type of network, broadcast or NBMA, during this, as a separate event, we will have gone through the DR-BDR election process. If either of us is DR or BDR, we will go on to the full state. So if and only if the two routers are DR other, so not DR, not BDR, then we'll stay here in the two-way state. Every other condition takes us to fully adjacent. So if we're going to go to fully adjacent, step 4 is X start. The X start state is an argument over who will begin the exchange process. So one router may say to the other, I will begin the exchange. I have the highest router ID. And the other one will either agree or disagree. But pretty quickly, they'll figure out who's going to begin. Then we move to the exchange state. In the exchange state, we begin to exchange our routing information, and it does it in kind of an index format. So the analogy I use for this is a library. I'm going to send you what's called a DBD. It's a database description packet. So in the library analogy, that would be a drawer from the card catalog. So if you're in a library and you pull out the drawer of the card catalog and you look at one of the cards, what you're holding there isn't the book itself. It's a pointer that says that that book exists in this library. And it's very similar to what a DVD is. So I'm going to send you my A drawer. You're going to send me your A drawer. That happens in the exchange process. So we both process all these cards. So I'm going through these cards. I'm looking for books that you have that I don't have. When I find one, I set it aside in a pile. And this goes on until we've exhausted all cards in the card catalog. So at the end of the exchange process, both of us have a pile of these cards representing books the other library has that we don't have. And remember, the whole goal of this is for us to have an identical database. So in this case, we want our libraries to be identical. Then we move to the loading phase. In the loading phase, I take one of these cards off the pile and I send it to you and I say, get me a copy of this book, please. And I'm going to ask you with the link state request. And you're going to send me the book with the link state update. And this process will go on bidirectionally until the two libraries are the same. And these DBDs and LSRs and LSUs are all reliable packets, so we will acknowledge them where appropriate. So at the end of this process, when we're in the fully adjacent state, libraries are identical, or our OSPF databases are the same. So that's a lot. I imagine that you'll have to go back to the recording and watch this a few times, but there's a lot of opportunity for test questions here. You want to make sure you understand all of this.